say a function. F of x is 1 to 1. If f of x1 is not equal to f of x2, say f of x1 is not equal to f of x2 when x1 is not equal to x2. So what I'm saying here, two y values cannot be equal if the x values are not equal, which is another way of saying I cannot repeat y values here. So we talked about functions, we can't repeat x values. For a one-to-one function, we can't repeat y values. So to see this, a lot of times we'll use what's called the horizontal line test, and this tells us if I can draw a horizontal line and it touches the graph twice, then I'm going to have some repeating y values, and then it's not a one-to-one function. But we're not going to focus on that too much. What we're really going to look at today is how that applies to inverse functions. So let me just give you a few examples of one-to-one functions. If I have, let's say, the square root of x, that'd be a one-to-one function. If I had x squared and I restricted the domain to say that x was greater than 0, that would be a one-to-one function. But only if x is greater than or equal to 0 or some domain that I ensure those y values don't repeat. Okay. And then we'll do one last example. Let's say I have the absolute value of x, and I'll say if x is less than or equal to 0. So the absolute value would not be a one-to-one function, but if I restrict that domain to x is less than or equal to 0, it's going to be okay because we'll only have negative x values. So really this is the same thing as saying just negative x. So let's define an inverse of a function. So an inverse. Let's suppose f is 1 to 1 on a domain D. So on a specified domain, we have a one-to-one function. The inverse we denote as f to the minus 1. So not to the negative 1 power. The inverse is defined by f inverse of b is equal to a if f of a is equal to b. And this implies the domain of f is the range of f inverse and vice versa. Meaning the domain of f inverse is the range of f. Right. So mostly we're going to find inverses by switching those x and y values. And that's what we can imply from this definition. The x values of f are the y values of f inverse. So if I want to solve for an inverse, I can just switch x and y. So let's look at an example. Let's say I want to find the inverse of f of x is equal to 1/2 x plus 1. So we can write this as y equals 1/2 x plus 1. We're just saying f of x telling us that f is a function. We'll replace f of x with y, and let's go ahead and switch those x and y's. So now that I've switched x and y, this is now our inverse. But we don't want to write x equals 1/2 y plus 1. We want to solve for y, and then we'll have our function. So let's subtract 1 from both sides. So I have x minus 1 is equal to 1/2 y. And then I want to isolate my y, so I should multiply both sides by 2. So I have 2 times x minus 1 is equal to y, or 2x minus 2 is equal to y. So we could say that f inverse of x now is equal to 2x minus 2. Let's do one more. So let's say I just said y equals x squared. If I said y equals x squared, there is no inverse, since y equals x squared is not a one-to-one function. But let's say I add this extra piece of information. Let's make x positive. It could be equal to 0 as well, but let's just say x is positive. So we're going to do the same thing. So I'm going to switch my x and y values now. So I got x equals y squared. From x equals y squared, we can take the square root of both sides. So this is the same thing as saying the square root of x is equal to y. And we're allowed to just say y and not plus or minus y because I said x is greater than or equal to 0. So it is implied that our y values here from our definition of inverse functions have to be positive because the domain of f inverse is the range of f and vice versa. So we're all okay here. We don't have to worry about the minus y here. So our inverse would be the square root of x is equal to y. Right. So we oftentimes use inverse functions because it helps out with our natural logs and our log functions. So let's now go ahead and define a log function. We mentioned this briefly before when we were looking at the graphs, when we switch those x and y values in order to graph y equals log 2x. Formally, we can define a log function as the log with base a is written log a of x and is the inverse of the base a exponential y equals a to the x. So let's say this is y equals log a of x. So y equals log a of x and y equals a to the x are inverses, which we saw when we graphed those earlier on. All right. So let's just add some extra helpful definitions here. This is also true for the natural log. If I have the ln x is equal to y, this is an equivalent of saying e to the y is equal to x. From this information here, we can see that ln x and e to the x would then be inverses. And then one helpful property we're going to use a lot in this class, not super related, but since we're talking about logs, we should note that the ln of e is equal to 1. If I have base e and I take the natural log, if I have e to some power equaling e, clearly it would have to be 1. Okay, so let's use some properties of logs now. Some properties we're going to use, I'm going to write them all with the natural log. You could replace the natural log with log without changing anything. But first off, let's look at our product rule. So I have ln bx. So b and x are variables here. So having two things being multiplied together is the same thing as adding them as two separate logs. So ln b plus ln x. If I have the ln of b divided by x, this is the ln of b minus the ln of x. So that's our product and quotient. We're going to oftentimes use the reciprocal rule, meaning if I have ln 1 over x, this is the same thing as saying negative ln x. Because ln x to the negative 1, we're allowed to move powers to the front. So this is the same kind of concept as our power rule. It's just for any power, in this case, not just the negative 1 power. So if I have ln x to the r, this is the same thing as r ln x. Right. So we're going to use these to find. We're going to use these properties to combine and expand some different logs. So let's say we have the ln 4 plus ln of sine x. I have two logs that I'm going to add together. This is the same thing as multiplying them. So this would be the same thing as ln 4 sine x. Let's say I have ln x plus 1 over 2x minus 3. I'm also able to expand this. This would be the ln of x plus 1 minus the ln of 2x minus 3. So I can change division into subtraction. If I have ln 1/8, I can use my reciprocal rule. This is the same thing as saying minus ln 8. I could rewrite 8 even as minus ln to the 2 to the third, which would make this minus 3 ln 2. So that'd be the most simplified version. Oftentimes we wouldn't do that, but all these rules do apply. So I might give you some practice problems using these rules. You just want to be able to add them together and change it to one log when you're multiplying, or vice versa. If I'm giving you something multiplied together, you're going to expand them into adding two logs. There might be some power rules we could practice, but these are the main rules I'm going to test you on, maybe just one question or so. Not going to focus too much about logs now. They'll come back up a little later on. I just wanted to introduce them. All right, that's going to be it for today. It's just a little overview, and I hope everyone has a great day.